Hello, everyone. So my name is Menachem Moshelion. I'm from the Hebrew University, Faculty of Agriculture. I'm a plant physiologist. I would like to thank Jeff for this beautiful introduction. You see that after many years of research, the explanation is always physiological. And to me, as a plant physiologist, I want to show you a research doing in the last almost 2 decades of trying to find this physiological characteristic in a high throughput manner at the early stages. So you can predict the production of a plant much before you go to the field. I mean, you have to go to the field, but we have to screen thousands of genes and interactions. So we all know this is the basic principle: plant lose water and gain CO2. There is nothing too much we can do about it, because if we reduce the water loss, we also reduce gain. And this principle of water use efficiency, it's something that is very hard to play successfully. It's more on the plasticity we need to play, and this is what I want to talk today. So this ratio of 500 to 1, we have a pointer here? It's pretty much an average, right? I'm going today in my talk to talk mainly on tomatoes. It's true for tomatoes. And when you look on the developmental phases of a plant, you can see clearly 2 main phases: vegetative and reproductive. Now, during the vegetative plant are producing leaves, they're growing in height, and the blue line here is the transpiration, the total transpiration. You can see the total transpiration goes very nice with the height and the leaves. But then at this stage, when the plants start to flower, the transpiration became steady because the new leaf are almost do not develop, or there is a balance between all the non-function leaf and a new leaf. And if you calculate the water use efficiency from this growth rate versus the water transpiration, I mean the green line, the biomass gain, and the blue line, the water loss, this is the water use efficiency you get in the vegetative phase. And it's getting much worse under reproductive. You see the slope is much less steep. So basically, if you get drought at this part, so if you don't get drought, pretty much the higher you can get here in transpiration, the better is your yield going to be. So in fact, we can screen here for about 2 weeks, and we have a great prediction about the yield. Of course, if you have stress here, you have much less leaf and much less productivity, so you're going to expect to have much less production in the yield. Of course, we can do the same in the productive, but today I want to talk mainly on the vegetative phase, because this is a better place for screening because it's just come earlier, so it's much easier to do. So what is drought response, basically, okay? I want to show you some simple experiment we did. So we took tomato plants, we just followed the transpiration rate, and when they reach about 500 ml per day, it's a very small plant, like 3 weeks or 4 weeks plant, very small plant. We reduced the water they get to 160 ml per day. That's it, about 1/3 of what they can transpire. So the plant can lose about 500 water. This is the capacity of water loss. But it just got 160, and like in 3-4 days, look, he reached 160. He used exactly the amount we gave it. And then we measure the recovery. Recovery means we just give it as much water as needed. Look how fast the plant recover. We decide to do it with much more concentration. So we use our Plant-DiTech system. So each plant is sitting on a balance. So we can automatically irrigate each plant in the exact amount you want. So we literally screen hundreds of plants and gave each one of them different water level from 100 ml per day to 500 ml per day. And look how nice the plant orange, this is 20 ml difference, 20 ml. Look how nice the plant can use the exact amount they got. It's like pretty long drought. And then in the recovery, look how nice they recover. I will talk about recovery later because I think this is one of the most important traits. So I will leave this for later. Now, when you look on it, you can see that under drought, the plant uses every ml. I want to prove this. So if we take the rate of water given to the weight of water loss, look about this graph. Look how nice the graph is. This is how much water the plant actually uses. You can see this is the R square, R99. So the efficiency is about 0.95. We always say that plant use about 95% of the water, or sorry, they lose about 95% of the water and they use about 5. Look at the last number, it's about right. So the rest of 6-7% they use for photosynthesis. Okay, so we can clearly say that plants are opportunists. They don't leave any reserve. You give them water, they use it. And the resolution is amazing. We play with 20 ml differences, 20 ml in 4-liter pot. They just use it all. So if plants are opportunists, how exactly are they using this water? So this is the same plant, only on a daily scale or momentary scale. So this is the rate, sorry. This is the rate of the water loss at this point, okay? We just took, instead of daily water loss, we took momentarily water loss. And you can see very clearly that even the 100 ml doesn't just lose the water, it just loses it all over the day. So the stomatal response have a very crucial role about how fast the plant uses it. So at this plant uses 100 ml and this plant uses 500 ml, but the strategy is very different, probably because of ABA accumulating in the leaf. And of course, when we took all the plants, you can see all of them are under exact same condition on one table, seeing the same VPD, the same light, only different irrigation. So of course, if this is the strategy, we decide to work on tomato inbred line. We got it from Professor Dani Zamir with 30 lines. And what we did is a reverse phenotyping. So we wanted to have a lot of yield coming from the field for many years. So Dani Zamir was kind enough to give us this library from the field, of course, yield biomass. We took this data and we used these plants. I mean, we screened the plants and we monitor them to high yielding under any condition. This is line 5.2, remember the name, and these 2.6, these are idiotype. What do I mean by idiotype? In the field, for at least 4 to 5 years, they produce more yield, sometimes more biomass, sometimes not. And we also took, of course, some bad ones. Look at this 18.1, just for example. And we screened those lines. Again, what we did, we control the irrigation base with the lysimeter system. Each plant was measured the soil water content and the VPD above it and the light. And of course, was irrigated based on his own transpiration. So we could really control the drought. Many people ask me why we use these funny looking green buckets. This is to prevent this water loss. You know, when you irrigate your plants and you just let water loose, here you have much more than 20 ml loss. And I show you the plant sends milliliter. So you really have to keep each ml counts. So you don't want to use this underline or this cover. So this is why we use these green buses. Also, this allows us, the system, to separate between the shoot transpiration, root flux, and water in the soil. So we actually have 3 different of the puzzles separately. We can use each one differently, and we can do it continuously and simultaneously to all the plant together. We measure biomass, transpiration, water use efficiency, stomatal conductance to the whole canopy. I want to mention all of these parameters we measure are absolute, which mean real numbers, ml per minute, and to the whole canopy, not coming with a Lycor. It's the whole plant, which I think is much more important. Perfect. We took all the data, I can skip this. I'm not going to get how we did it. The way to take whole plant canopy conductance, water use efficiency, this was published by ourselves and other collaborators from Wageningen. So you can check the algorithm. They're working very nice. So I'm not going to get into details. I just want to show you some results. So this is the 18.1. Remember, this is a bed plant. This is the transpiration rate daily. I think the daily transpiration is one of the most important key physiological characteristics of a plant. When you compare it to the 5.2, look the difference in like 2 weeks. Look the vigor of this plant compared to this plant. This is in 2 weeks. So you already have a very important trait to screen for. This is the M82. And these are all the other lines. You can see significant in 2 or 3 days, you start to see significance, but this is before drought, okay? Now the question is how to do drought. When you take the all interrogation line population and just close the tab, this is the drought effect you get. It's a mess. You cannot compare plants under drought, especially not in pots, when you just close the tab, because that means that each plant going to sense a very different stress scenario. So you don't really compare stress to stress. So what we did here, if you want to compare stress to stress, all the plant has to be stressed in the same way. So what we did, we used the algorithm of the PlantArray that enable us to do dehydration, controlled dehydration. You remember each plant is sitting on a lysimeter and have a feedback irrigation. The system knows to keep each plant under the same soil water gradient. Now, why do we use gradient? When I say gradient, I mean this, and not a steady state water like I showed you before, because this is a real scenario from the field. In the field, plant dry down slowly. We just saw a picture from Jeff, you can see it. So we want to imitate the dry down as in the field. So all the plants have to get their same dry down, but because each of them transpire differently, you have to control it. So the stress is very nice. I want to talk also about the recovery. You see, after the stress, we recover the plant, and you can clearly see the difference in the recovery rate. Look at the productive line recovery rate versus the 5.2 versus the 8.1. The 5.2 is the ideal type, the 8.1 is the not so good one. Look the huge differences in the penalty. The penalty is the rate of recovery. So the rate of recovery basically tell you how much the plant suffered during the drought. As more the plant suffer, the better its recovery. Sorry, if both plants suffer the same because we control the stress and this one recover faster, we have less penalty and more yield. Another important issue, what is drought? I mean, we talk about drought all the time, but what is the drought point? How do you know that this plant now is suffering from drought? What we did here, we actually look at this graph, which check the point, we call it the theta crit, that the transpiration start to reduce. So we look on the soil water content, not the time, the soil water content, where you start to see reduction in stomatal conductance. Of course, we did it to all the plants, and we took a similar way to compare again the stomatal conductance versus the water loss. So this is stomatal conductance. Stomatal conductance means how much the stomata is open. Transpiration means how much it actually loses. It's different calculations. Stomatal conductance is very important because it actually tells you how much CO2 the plant can gain. And look at this. This is 5.2. Okay, this is the stomatal conductance. Look at this difference. This difference means that the stomata is more open at early time of the day here when the VPD is low, but the light is enough. So what we see here is a daily water use efficiency. The plants are much more flexible. They use the same water, the same light, but in a different approach, in much more plastic approach. These kinetics actually bring more yield in the end. I'm sorry, I have to rush. Yeah. So we check the stomata itself. This is by the way on bioarchive, so you can look at it. And the main difference was the difference in stomatal density. You see, this is the lower part of the leaf, and this is the upper part of the leaf. This is 5.2 and 8.1, this is the high yielder. They have much more stomata on the lower part of the leaf. And this is the actual aperture. We went and measured the true aperture of the stem. Look the time that the stomata is open in the 5.2 and look at the time the stomata open in 8.1. So the 8.1 opened the widely the stomata at noon, and the 5.2 widely open it in the morning. So this explains you the pattern we saw before. Of course, we did it to all the plants. I'm going to skip the gene, but we find also genes that are related. Let's go to the conclusions. This is the most important. So we want to know what is the stomatal aperture. This is impossible to do in the field. So we also want to know the density between the abaxial and the apaxial. It's a hard working. We also want to see what's happening in the dynamic of the environment. Remember, the environment changing every minute. So what we saw that this stomatal conductance that we measure with the system actually give us all of this together, because the conductance of the plant actually reflect the environmental condition, the density in both places, and the true aperture. You can see this speak in many other papers. I'm going to skip it. Conclusion. So if you want to look, what are the best parameters to look in a pre-screening like we do here? And I'm talking 3 to 4 weeks, that's it. We want to find high transpiration plants. We want to see fast closure. We want to see very nice plasticity of the stomata, especially wide opening when the VPD is low. We want to see much more stomata on the bottom part than the upper part. And we want to have this plastic behavior of much wider opening at early time of the day. And we want to see very good recovery rate. Recovery rate actually represent all the drought in one single trait. So the drought response in the recovery is the best trait that reflects the drought response, to my opinion. Okay, I just want to thank Sanbon Gosa that actually did the paper, Dan Izami that gave me the library, Ohad, Bogale, Ravi, and Ramon that actually was master student help. And thank you.